Hello, good afternoon to everybody. It's with great pleasure that as a dual role, I'm here in a dual role as the Pro Director of Science and Culture, representing the Director of the Faculty of Sciences of the University of Porto, who for health reasons cannot be here today with us. And as Professor of Mathematics at this institution, I welcome all of you to this event, Mathematics and Hope, Levers of Innovation, which today marks and celebrates the International Day of Mathematics, or Pi Day. Allow me to begin by extending a very special greeting to the Minister of Education, Science and Innovation, Professor Fernando Alexandre, who honored us with his presence and his participation in the closing round table. I'm also very pleased to greet Vice-Rector Ana Maria Camanho, representing the Rector of the University of Porto, the President of the Lisbon Academy of Sciences, Professor José Francisco Rodrigues, the Vice Rector of the University of Porto Research and Innovation, Professor Pedro Rodrigues, who is not here yet, the Director of Faculty of Economics at the University of Porto, Professor Oscar Afonso, the President of the International Center of Mathematics, my colleague and friend, Professor Jorge Freitas, and Director of Center of Mathematics of the University of Porto, Professor Helena Reis. Our distinguished speakers that I'll introduce later, members of the academic and scientific community, and all those here present who join us today at this event. This International Day of Mathematics event is organized by the Lisbon Academy of Sciences, the International Center for Mathematics, and the Center for Mathematics of the University of Porto, and aims to reinforce the fundamental and often invisible role of mathematics in the development of science, technology, and innovation. That's a problem with mathematics. It's greatly invisible. Also invincible too. From theoretical advances to real-world applications, mathematical ideas underpin progress across a wide range of fields, including artificial intelligence, engineering, data science, and industrial optimization. At the same time, mathematics fosters rigorous thinking, creativity. It's very hard to explain to laymen that mathematicians are very creative. I had some trouble with it, but they do, and as all of you here know. And long-term vision, essential ingredients for addressing complex challenges and shaping a sustainable future. This event aims to raise public awareness of the central role of mathematics as a driving force behind innovation and scientific development. By bringing together researchers with diverse trajectories, spanning fundamental research, interdisciplinary work, industry, and scientific leadership, the program highlights how mathematics serves as a powerful lever for knowledge creation, technological progress, and societal impact. So this section will consist of short invited talks, followed by a roundtable discussion, encouraging the dialogue between different perspectives on how mathematics contributes to innovation, opportunity, and hope. And I should mention that this initiative has the support of the Institut Français de Portugal and the University of Porto. So I open the session. To open session, I have the great pleasure of inviting the Vice Rector of Digital Information and Information Management of the University of Porto, Professor Ana Maria Camacho, to speak on behalf of the Rector of the University of Porto.
Excelentíssimo Sr. Ministro da Educação, Ciência e Inovação, Professor Fernando Alexandre, Excelentíssimo Sr. Presidente da Academia de Ciências de Lisboa, Professor José Francisco Rodrigues, Excelentíssimo Sr. Presidente do Centro Internacional de Matemática, Professor Jorge Milhazes de Freitas, caros professores Jean-Pierre Bourguignon, Professor João Ribeiro, Professor Nguyen Tien Dung, Professor Eugênio Rocha e Professor Pedro Camanho, caros participantes nesta jornada. It's a privilege for me to welcome you on behalf of the Rector of the University of Porto to our Faculty of Sciences and to this event, organized jointly as an initiative of the Lisbon Academy of Sciences, the International Centre of Mathematics, the Centre of Mathematics of the University of Porto, with the support of the Faculty of Sciences. As you know, this event is part of the celebration of the International Day of Mathematics, which is commemorated on the day whose English notation reflects the value of the first 3 digits of pi, 3.14 or March 14. We are particularly pleased to host this event at what is, according to international rankings, a nationally and internationally recognized institution for university-led mathematics education, therefore contributing significantly to the prestige of the University of Porto. We are also proud that in this field we are able to attract some of the best secondary school students and, thanks to the work of our professors and researchers, help them realize their full potential by providing an education of high technical, scientific and ethical quality. This is work that we strive to begin even earlier, including at the pre-university level. A decisive contribution in this regard comes from the Universidade Júnior initiative, through which we aim to strengthen the scientific culture of young people from across the country by bringing them together in contact with the work carried out at university, the career paths opened by each degree program, and the practical realities of professions associated with different fields of knowledge, including, of course, mathematics. We do this first and foremost because we recognize the central role of mathematics in the scientific and technological development of innovation in our time. We also do so because we fully understand the importance of attracting and nurturing talent in this field, which today is closely connected with the information and computing sciences and technologies that are widely used across many different areas of knowledge. In this way, we seek to fulfill even more fully the essential mission of the university, to educate those who will imagine the future of our communities, equipping them not only with the technical and scientific tools, but also with the ethical foundations needed to shape a more promising future for all. At a time when, perhaps more than ever before, mathematics intersects so intensively with so many fields of knowledge, the emphasis placed on the ethical dimension of the education we provide is far from a mere formality. If, as suggested in the title of this event, mathematics is today intrinsically linked to the word hope, then that hope must also be closely tied to its responsible use and to the ethical principles that guide its many applications. Allow me, therefore, on behalf of the Rector of the University of Porto, to express our hope that this meeting will prove highly fruitful and help ensure that innovation driven by mathematics truly becomes a source of hope. Thank you very much.
Thank you, Professor Ana Camanho. So now I call on the President of the Lisbon Academy of Sciences, Professor José Francisco Rodrigues, to give his address.
Thank you. Mr. Minister, Mr. Vice Rector, Mr. Director of SIM, all colleagues and friends here. It is a pleasure to be here today at this occasion on speaking or opening this on mathematics and hopes levers of innovation at P-Day in 2026. And maybe you should know that at the proposal and an initiative, the International Mathematical Union, the UNESCO General Conference at its 16th plenary meeting in 25th November 2019 proclaimed this day, March 14th of each year, the International Mathematics Day, also called P-Day. Among considerations underlying this decision is the recognition, and I quote, global awareness of enhanced education in mathematical sciences are vital to addressing challenges in areas such as artificial intelligence, climate change, energy, and sustainable development, and to improve the quality of life in both development and developing worlds. And a little longer, also quoting, the types of engineering computer science while responding to the growing needs of automation and providing access to information in the internet, the World Wide Web, for the well-being of society. End of quotation. Last year, for the first time, the Academy of Science of Lisbon celebrated the P-Day, dedicated to mathematics and creativity. That was last year's topic. With the conference promoted by its Young Scientist Seminar and the presentation of the awards of a competition that the Academy of Science promote together with the Ciência Viva, together with Portugal Society and Lisbon Society of Lisbon, about the competition on the 5 missing symmetries of Lisbon Calçada. As you may know, there are only possible 24, and Lisbon has at this moment all but 5. And there were beautiful results, and laureate students were students of grades 9 to 12. Last year also, in 2025, the Academy of Science established an agreement with the Centro Internacional de Matemática and with the University of Porto. So this year was natural to organize with these 2 institutions the Pi Day to celebrate this challenging association between mathematics and hope as an essential levers of innovation. We know that mathematics, as the science of numbers, patterns, and proofs, is the essential foundation of the progress of knowledge and innovation. We see today how many modern technologies and innovations were generated from mathematical ideas that once seemed pure, theoretical, and even useless. Number theory, once viewed as a pure intellectual conundrum, now secure global communication through cryptography. Linear algebra is the engine of machine learning and artificial intelligence. Optimization theory propels logistics networks, energy systems, modern engineering, and economics. Mathematics offers not only the technical solutions and the formal approaches for the engineering and economic problems, but also provides the foundation for evidence-based decisions and policies. Mathematics does not only describe the world, it is also a foundation for creativity, discovery, and progress to help create the future. Hope, as a proactive state of mind, combines a desire for beneficial outcome with the belief that it is possible, even when it is not certain. It is not just an emotion or wishful thinking. It is an active, a raison d'être, that drives people to plan and work towards a better future, often acting as a key to resilience and perseverance during adverse times. Mathematicians work on models or in proofs for months, years, because they believe that the structure of truth is there to be discovered and to solve the problems. Innovators build new prototypes and iterate new designs because they believe that a better solution is within reach. For mathematicians and innovators, hope is the confidence that complex problems, through careful reasoning and creative thinking, can eventually have solutions. Mathematicians work on the language and the tools to understand complexity. Innovators provide courage and the skills to apply the understanding in new ways and daring initiatives. The collaboration between mathematicians and innovators has never been more important. We hope that the new mathematical ideas will produce breakthrough in science and technology. We hope that creative innovation will transform abstract ideas into practical and successful development. We hope that future generations will inherit tools and knowledge to solve problems we cannot solve today. Thank you.
Thank you, José Francisco. So to close this opening ceremony, I invite President of the International Center of Mathematics, Jorge Freitas, to make his intervention.
Thank you. Thank you very much. Okay. So today we celebrate Pi Day. So I went to Pi Day's official website and I looked for the explanation for the subtitle, because this year it's HOPE, Mathematics and Hope. Okay. Here's what they say. Thales said, "Hope is the most universal of all human possessions. More than 2,500 years later, we can also say that mathematics is one of the most universal human possessions." Okay? So let me elaborate a little bit further on this, and I'll do what I learned from my dear friend and my professor, Maquiavelo, and I'll give you a couple of examples about how mathematics is important and helps humanity. Okay? So first, I'll just jump like 2,500 years ago and talk about Thales. Okay? Thales from Mileto. I think most of you have learned the theorem of Thales. Okay? It makes a parallelism between triangles and all these sort of things, right? And he's famous for a story, which you don't know if it's true, but, well, for this purpose, it's perfect, okay? So the wise men in Egypt were trying to estimate the height of a pyramid, okay? And they were trying, this was a hard problem, right? The pyramids are very high and they like to estimate this. So Thales came up with an idea, which of course is underlying his theorem, which was basically the following. He lay down on the floor and he marked his height. And he waited until the sun would make a shadow as high as his height, or as long as his height. And then at the same time, he went running and measured the length of the shadow of the pyramid, and then said, that's its height. Because, why? There is a proportionality here. So when the shadow of his height is the same, then the shadow of the pyramid is going to give you the height of the pyramid. Okay? So this is mathematical thinking at the best. So it's one of the best examples. So the second example I bring here is from a theorem of 1957. And its title is On the Representation of Continuous Functions of Several Variables by Superposition of Continuous Functions of One Variable and Addition. Okay? Simple title by no other than Kolmogorov and Arnold. Okay? And this was done in 1957, right? And one can think, okay, most of you in the audience are mathematicians, so you must have read a lot of theorems that look like this, right? In analysis courses, I've seen hundreds of theorems that look like this. Maybe none of them has now the applications that this theorem has today. And I'm sure that when it was proved, no one was figuring out the impact it would have today. Well, today, ladies and gentlemen, this theorem is the core, is the pillar where Kolmogorov-Arnold networks build on. Okay? So, for example, in artificial intelligence, we have MLPs, and we have now CAN networks. And this is the theorem where everything is based. And the point is, when it was done, when it was proved, no one expected that it would have this application today. Okay? And this is the beauty of mathematics. And this is the beauty of basic science. Is the fact that sometimes people just do things because they enjoy it. And sometimes this is like what Eric Lander called the magic machine, because it pays out. Maybe it doesn't pay out immediately, but in the long term, it pays out. And the point is, sometimes you can't figure it out, or you can't know exactly where is this disruption going to appear. But we know there will be disruptions coming from this sort of knowledge. Okay, so these are the two examples I had, and I hope you enjoy your time here. And I finish my intervention here. Thank you.
So thank you, George. So now we'll start with the interventions by our guest speakers. We have here gathered today a group of very distinguished, let me correct this, extremely distinguished speakers who will share their perspective on the relationship between mathematics and innovation and the hope for the future. So let me start by presenting our first speaker. We was already here, and I had the joy of hearing him speak 2 years ago. I don't remember, but it was an amazing talk. I remember the talk, not when it was. Professor Jean-Pierre Bourguignon, a French mathematician whose main work is in differential geometry with a focus on geometric questions at the interface of theoretical physics. He graduated from the École Polytechnique and got his PhD degree at the University of Paris Diderot. He was director of the Institut des Études Scientifiques for almost 2 decades. He was second president of the European Mathematical Society and later became president of the European Research Council. Widely recognized for his role in promoting mathematical excellence and long-term scientific vision, he has received numerous international distinctions and is an honorary or foreign member of several academies and scientific societies. I think one of them is the Academy of Science of Lisbon. It's a great honor to have him here today, and I call on Professor Bourguignon to give his address.
I'm sorry, but my lecture has disappeared. So I need to get to my computer. Is it this floor? I'm sorry.
It's okay, it's okay, it's okay.
It just disappeared.
So let's wait a little bit. So meanwhile, you can memorize the digits of pi.
I can tell another story if you want.
Okay.
Okay, of course, but mathematics is everywhere. Maybe this is a more funny story. So the other day I was just listening in the car a podcast, and they were talking about how Jimmy Arias introduced the top spin movement in tennis. Okay, I don't know if you play tennis, but this is an important move that every day all players use it. And then they mentioned that he learned it from his father, not from his coach. And his father was a mathematician. And of course, he knew physics. And well, actually, there is a dispute. If you go to internet, yesterday I had a discussion with ChatGPT because some say he's a mathematician, some say he's in electrical engineering. Well, it doesn't really matter where he comes from. But the point is that he knew physics, and then he knew that he had to hit the ball and try to make it a spin so that it would bounce very fast. Okay, and it's like knowledge from physics or applied mathematics, engineering, or whatever can make a difference in so many cases, like in sports, right? Of course, I told my son this story, right, because he's a fan of Alcaraz. And then I thought, because we have discussions when he was growing, that I was always telling mathematics is everywhere. At some point, he was annoyed with this everywhere thing. So I'm always trying to show him that mathematics is really everywhere. And then he said that, and I said, so you see, do you know the moral of the story? And he says, okay, mathematics is everywhere. And no, some people pay attention to their dads.
Okay. So we think it's best to switch the order of the presentations, okay, while we wait for Professor Bourguignon. So we go to the second speaker, who became the first now, João Ribeiro. He's assistant professor in the Department of Mathematics at Instituto Superior Técnico with a doctorate degree from Imperial College London. He's a researcher at the Institute to the Telecommunications Institute, linking mathematics, computer science, and electric engineering through his training in applied mathematics and computer science. His research focuses on coding theory, cryptography, information theory, and pseudo-randomness, areas where deep mathematical ideas underpin modern digital security and communication. Following postdoctoral work at Carnegie Mellon and research stays at several renowned international institutions, he was recently being awarded an European Research Council starting grant, which is a very big thing, okay? So, Professor João Ribeiro, please.
Okay, microphone.
Oh, okay.
Can you guys hear me? Yeah? All right, cool. Yeah, thanks for the nice introduction, and thank you for the invitation. And also thank you, everyone, for being here. Okay, so I'll tell you, I'll use these 15 minutes to basically tell you a story about how math comes up in like real-world systems that are used by millions of people. Okay, I'll start by saying some very obvious things. Okay, the first thing is that math has had a tremendous impact on communication and data processing technology. Okay, and in, I'd say, multiple ways. One way is that it helps us formalize what we aim to achieve. And if you spend a bit of time thinking about how to formalize these tasks with mathematics, you see that this is a really interesting and fundamental mathematical challenges as well. The second thing is that then we can use techniques from other areas of mathematics, like algebra, geometry, number theory, and so on, to help us understand what are the fundamental limits of this communication and data processing tasks. Okay, and lastly, we can also use these same techniques, but maybe more optimized and in like smarter ways, to actually design solutions that can be used in practice. Okay, so this is basically usually how the pipeline works. Okay, so today I'll tell you a very concrete story that kind of touches these 3 points. Okay, and so I'll tell you about proofs. Okay, and proofs are a big part of mathematics. Okay, it's how you convince someone that something is true. But they're also mathematical objects. Okay, so they can be the subject of mathematical study themselves, and exploring or kind of reflecting on what it means to actually prove something, okay, kind of went from philosophy to something that's implemented in large-scale, highly efficient systems in about 30 to 35 years, okay? So let me first introduce the 2 main characters of our story. So there's Arthur. Arthur is the weak verifier, so he wants to understand whether a certain statement is true, okay? But he's very slow and he's very stupid, okay? So he's like me. And then there's Merlin, who's the powerful prover. So he has all the time in the world and all the memory in the world to try to convince Arthur that something is true, okay? So as an example, Arthur can ask, can every even integer be written larger than 2, be written as a sum of 2 primes, okay? And then Merlin knows everything, so he just sends him like a proof. And for you, a proof is kind of like a logical deduction of the statement from some axioms, okay? And Arthur thinks for a long time, and then says, okay, I'm convinced this is true, okay? So this is usually how the traditional proofs go, right? Okay, we can think about this a bit more broadly, okay? It's not about just kind of theorems, but could be any statement, okay? Let's say Arthur has a map of Europe and is interested in understanding whether he can visit, a list of cities in at most 500 kilometers, okay? For those who know, this is called the traveling salesman problem, okay? This is also like a statement you can try to prove, right? And here, what does a proof look like? Okay, Merlin has all the time in the world. He, brute forces over all the solutions, sends him kind of a path through all the cities, and now, Arthur can verify because he just like computes the total length of this path. It's at most 500 kilometers, okay? So he's convinced this is true, okay? So what's happening here is that if the statement is true, there is a proof that convinces Arthur. If the statement is false, then no proof convinces Arthur, okay? So that's the traditional notion of proof. Now, if you think about this, some natural questions arise if you're like, if you study the theory of computation. The first one is, which statements have what I would call efficiently checkable proofs. Okay, so like the traveling salesman problem has an efficiently checkable proof because it's very easy for me. You know, if I'm given a list of cities and the path through all these cities, I can just compute the total length and I'm convinced whether the statement is true or not, right? Either I'm convinced that the statement is true or I'm not convinced, okay? And there's a name for the set of such statements. It's called NP, okay? NP stands for non-deterministic polynomial time, doesn't matter. And I just want to draw your attention to, I said here efficiently checkable proofs. This is the word I use for like grant proposals. But like, here there's like a mathematician's notion of efficient, okay? Which means not practical at all. And then you can ask, you know, I mean, there's this duality between the statement being easy to verify, a proof being easy to verify, and a proof being easy to be produced, right? So you can ask, you know, if a statement has an efficiently checkable proof, is it also easy to prove, okay, to kind of produce this witness, okay? And this is called the P versus NP problem. You may have heard of it, like kind of high level. You get $1 million if you solve it. I guess you get a lot of things that are more important than $1 million if you solve it, but it's one of the 7 millennium problems, okay? And now our story really starts, which is that motivated by trying to understand this P versus NP problem, there was a set of researchers in the 80s that started to think about other possible notions of proof. Okay, is this like the traditional way of proving things? Is it the only meaningful notion of proof? And they consider some sort of relaxation. Okay, and for example, what if we allow the prover and the verifier, so Arthur and Merlin, to talk? Right, that's kind of how we discuss things in real life. Okay, so it makes sense to allow them to interact. What if you allow randomness? What if you allow Arthur to toss coins and make choices based on those coin tosses? Okay. And what if we allow the verifier, so Arthur, to be convinced of a false statement with a very, very small probability? Okay. So these were the 3 main things that they thought about. And so now they get this alternative notion of proof. Okay. By the way, I mean, this was awarded the first Gödel Prize ever, 1993. Gödel Prize is basically for the most important papers in the theory of computation. So how do now interactive proofs look like? So now, Arthur has some die that he can toss and like just throw and just get some random numbers, okay? Again, Arthur wants to know whether a given statement is true. Merlin now gives him something, but now they can interact, okay? So they talk, and after this interaction, Arthur thinks for a bit, and then, okay, he says, okay, I'm convinced that statement is true based on this interaction. And now, the requirements change a bit. So first of all, if the statement is true, there should be an interaction that convinces Arthur. If the statement is false, then no matter the interaction, okay, Arthur should only be convinced with about 1% probability. Okay, and the 1% here, like, could be, it doesn't matter too much, but I think it's a good concrete number. So the first question you may ask is, we had this traditional notion of proof, now we have this relaxed notion, and does this help us prove more things according to this more relaxed notion? And there was some result in the 90s, or like early 90s, that said that actually, statements with efficient interactive proofs are exactly equal to statements that can be decided with not a lot of memory. And this result by itself, I think, is not very informative for you, but let me just draw a picture. So there's like statements with efficiently checkable proofs. It's like that small box there, and the statements. And now, because of this result, we know that statements with efficient interactive proofs is a much larger set. Okay, so we can prove things, can prove a lot more things efficiently by allowing this interaction. Okay, and in the process of thinking about interactive proofs, people started to realize that actually they would stumble onto, upon these proofs that had this very peculiar property. So they called it zero knowledge. Okay, what is a zero knowledge proof? So let's take an example. Again, Arthur asks, can I visit all these cities in at most 500 kilometers? Okay, they interact now, and then Arthur thinks for a bit, and he says, I'm convinced this is true, but actually now I have no idea how to actually go and visit all these cities in at most 500 kilometers. So it's a proof that convinces you but does not tell you what the proof, like what the solution looks like. Okay, and that sounds a bit weird. Okay, but here's an example that shows that zero knowledge proofs are very natural. Okay, let's say I don't have a deck of cards here, but let's say I'd like to prove to you that I'm holding a red card. So I have the rest of the deck is on the table. I have a card in my hand. So there are two ways I can do this. Okay, one way is I show you my card, and you see it's the king. It's the king of diamonds, so it's a red card. The other way is I take the rest of the remainder of the deck, and I just show you all the black cards, okay? And if you see that all the black cards are on your hand, right, then of course I'm holding a red card, but you don't know which one. So you're convinced that my statement is true, but you don't know which red card I'm actually holding, okay? All right, so let me just say that, of course, this is a very informal example, and actually, and you should do this exercise, like how do you formalize mathematically the property that, some sort of proof does not basically allow you to prove the same statement to someone else, right? So I convince you that something is true, but you cannot just run away and just go go convince someone else that statement is also true, okay? And that to me is a very, very important mathematical contribution. All right, so then you can ask, what can we prove in zero knowledge? Okay, and there was again a result also from the mid-80s that says that actually everything that has an efficiently checkable proof also has an efficient zero knowledge proof. Okay, and this opened the door in principle again to various applications. Okay, and I say in principle here because we didn't have practical solutions to any of this. Okay, this is all efficient in theory. Okay, so one application would be anonymous authentication. Okay, what is this? Well, I have a service and I have a client. Now the service is playing the role of the verifier, the client is playing the role of the prover. And the client holds this private certificate that says that he's like authorized to access something. Okay, so now they can interact, and then the service is convinced that the client holds a valid certificate and is authorized to access something, but he didn't learn anything about the certificate. Okay, so this means like the client is not revealing his identity. Also, you could use this to perform delegated computation, which is the following. Like say you have an expensive function you'd like to compute, but you're very weak. Okay, so you take the client, who's the verifier, wants to compute this function. He's very weak. The server, who's now the prover, is very powerful, and he also has some private information. Think about the server as like you're running like an LLM. Okay, W there is like the the weights of your model. Okay, that you don't want to reveal to the client. Okay, so what they could do then is the client sends X to the server, who is very powerful, can compute this expensive function. He sends back the output of this function, but now the server could be lying to the client, right? So now the server needs to convince the client that he did compute Y correctly. It should be f of XW. Okay, so they interact, and in the end, the client is convinced that indeed he got the correct output from the server, but he doesn't learn anything about this proprietary information W. Okay. But again, keep in mind that we're in 1986, and computers are slow. The internet is really not really there, so this was not relevant at all. Like people didn't think this was going to happen. And even if computers were fast, all the solutions so far would lead to very, very impractical systems. Okay, so they couldn't be used. So my conclusion from this is that practical applications were definitely not the motivation for this line of research. We're really just doing some sort of philosophizing about the fundamental limits of interaction and randomness in computation and communication. And if you don't really believe me, let me just tell you what the NSA had to say in 1992 about this. Okay, so this is from a very funny declassified internal report from the NSA on a crypto conference called Eurocrypt. It's one of the main cryptography conferences in the world. For those who don't know, the NSA is a national security agency in the United States. I will not discuss the morality of this agency. Feel free to ask me about it offline. But they are still, the reality is that they are one of the main developers and users of applied cryptography in the world. So, what they say about the applications of cryptography does matter. Okay, so here's what they had to say about zero knowledge in 1992. So those of you who know my prejudice against the zero knowledge wing of the philosophical camp will be surprised to hear that I enjoyed the 3 talks of the session better than any of that ilk that I had previously endured. The reason is simple. I took along some interesting reading material and ignored the speakers. Okay, so I think this kind of proves my point. Okay, I hope I've convinced you that this was all pretty useless. So then let me tell you what happened today. Okay, like about 30 years later, give or take, but now close to now 40. But like this, I guess this is stuff that already started being implemented about 10 years ago. So we have like Cloudflare. Cloudflare has tools that are trying to replace CAPTCHAs, which I guess you guys know. It's this thing you kind of do to prove that you're not a bot. Okay. But they want like an anonymous version of CAPTCHAs. And they have something called Privacy Pass, who has about 500K users. And I think it's being implemented by Google and Apple. There's Signal, which is like a kind of a private chat. So they have secure backups and private groups using zero knowledge. So basically you can like store information in their servers, but there's nothing linking your identity to your backup. Okay. They have about 40 million users each month. It's hard to estimate because it's all private, okay? It's all anonymous. Then there's the Brave browser, who uses zero knowledge to kind of provide, private ads to its users. So these are ads that don't really track, your identity, your profile, like your preferences. There's also Zcash, which is like a cryptocurrency, where they use very efficient zero knowledge proofs to basically anonymize transactions. Okay, so you cannot link, someone to a given transaction or to the amount of that transaction. Okay, so wrapping up, just mathematics has had a tremendous impact on communication data processing technology. I hope I've showed you, an example that was kind of something you didn't know before. Sometimes it's really tricky, but very rewarding to try to formalize these tasks mathematically, in particular, this concept of a zero knowledge proof. More generally, cryptography and coding and all this stuff, they basically uses beautiful math everywhere. Okay. We started about these problems way before they were relevant. Way before the application that people had thought about were relevant. And this math that is very beautiful is today the backbone of highly efficient cryptographic systems used by millions of people. And that's all from my side. Thanks.
Thank you, João. So now we go to Professor Jean-Pierre Bouignon talk, please.
My apologies for this. It's the first time this happens to me, although I've been using this for years. But anyway, I don't know why my telephone... Is it on? Or?
It's
on. No, I don't need the computer. No.
Oh, you don't need the computer? Okay.
No. I just need the microphone. Dear Minister Fernando Alexandre, the President of the Portuguese Academy of Sciences, Cher José Francisco, dear Vice Rectors, dear Director of SIM, dear Jorge, dear colleagues and friends, ladies and gentlemen, we're gathered here today, March 14, and in many other places in the world to celebrate Pi Day. This world event has been set up to recall that there was a fortunately unsuccessful attempt to normalize the value of pi in total disrespect of its scientific nature. This happened in 1897 in the Indiana House through a vote which should have given a legal basis to a series of unfounded claims of solution to several historical mathematical problems, such that trisecting an angle, doubling a cube, or squaring a circle. At the time, all these problems were known to mathematicians around the world to be unsolvable. The law aimed also at giving officially the simple but wrong value 3.14 for pi. fake news at its best. The wonderful history of pi, not sufficiently taught and cherished, tells us that getting what one now knows about the remarkable number pi has required contributions by people from many different cultures. Actually, it has been a truly universal human adventure, focused only on the search for truth, even if the interest in pi comes from a very practical problem, namely, as you know, relating the circumference of a circle to its radius. This story has been marked by a number of major hard-won surprises, thanks to the great ingenuity and creativity of many people all along the history of mankind. Today, we're living very special times during which one can witness massive attacks of an unprecedented level on painstakingly assembled knowledge. This happened through challenges of the scientific method, the rational approach it took scientists centuries to build in order to provide a solid foundation to their results. For me, in these days dominated by organized, I should probably even say militant, disinformation, the absolute priority for scientists is to make the value of science perceptible to the woman and the man in the street, in particular to the next generation. This priority is especially valid for mathematicians, whose science has such a long history and transcends cultures. Even the way it was developed has several cultural declinations. This year, the theme chosen to be coupled with mathematics during the Pi Day celebration is hope. Let me spend a couple of minutes discussing this choice, which could not immediately appear legitimate to some people. One first relation of hope to mathematics comes from interpreting it as positive expectation, something which calls for the help of mathematical models to reduce uncertainty, and when possible, for their use to transform a problematic situation into one with better expectations. Another relation connects hope to the way people relate or should relate to mathematics. It is a fact that today, having had the training which makes you possess a good familiarity with mathematical knowledge increases significantly your employability. The key issue to access this form of hope is to create the state of mind in pupils which makes them willing to do the personal investment, allowing them absorb this methodology and enabling them to use efficiently the tools it gives them access to. Both refer to the importance of rational thinking in the scholarly training and the value given to being comfortable with the exchange of arguments and ready to persevere if one encounters some difficulty. Acquiring this capacity is one of the central functions of schooling, and developing it should be one of the main focus in the training of teachers. I would like to have a look at the connections between mathematics and hope through three key lenses, captured by the following three verbal expressions. The first one is to understand, second one to be open and daring, and the third one to take advantage of emerging technologies. The domains they cover do overlap, but for the purpose of this short talk, let me consider them successively. I begin by to understand, and by what this means specifically for the number pi itself. Initially, the objective was just to estimate the value of this number. Here, I use deliberately the word estimate, since indeed the framework to discuss the deep nature of pi was not available. Over time, better and better approximations were available, up to the point that one knew enough about its true value to be sure that 3.14 is a value one should refer to if one insists on giving it only with two decimals. This was actually achieved by Archimedes more than 200 years before our era. Did this unveil the true nature of pi? Of course not, since at this time, no formula giving its value with an unlimited precision, possibly using an infinite process, was available, even if a method to do that was known without providing a result for the explicit computation. It took several centuries to achieve that level of depth, precisely until the German mathematician Ferdinand von Lindemann and Entschuldigung, proved in 1882 that pi is a transcendental number, which means that it is not solution of any algebraic equation with integral coefficients, and in particular an irrational number, assuring that there is no repetition in its decimal expansion. And therefore, by the way, this result by von Lindemann resolves in the negative the possibility of squaring a circle using only a compass and a ruler, the law I referred to in starting attempted to claim. Francis Bacon's Novum Organum, published in 1620, is often considered to be the foundational text about the scientific method. There, he argued, I'm quoting, "Nature can only be commended by obeying her." In other words, humanity can govern or direct the work of nature to produce definite results, but this requires understanding how nature works. Here is how he formulated it. Humanity would be raised above conditions of helplessness, poverty, and misery while coming into a condition of peace, prosperity, and security. End of quote. If one takes the time to compare the world in this age, the age of Bacon, with our own, he has proven spectacularly right, since indeed a lot has been achieved. Let us hope this doesn't get forgotten by too many people, particularly in political circles, as we can witness with huge concern today. The present state of the world, indeed, shows significant departures from the, quoting Bacon, condition of peace, prosperity, and security. And we see a frightening move away from rational thinking gain more and more attraction to many people in several countries. For sure, such a widespread phenomenon needs more in-depth research if one follows Bacon's requirement, namely to understand in order to be able to act efficiently. Let me now move to my second lens, namely to be open and daring. For it, I will start with a very personal recollection of the world event in which I was randomly a witness from a distance. Misha Brin is a Ukrainian mathematician who was trained in Moscow. He was a brilliant student of Yakov Sinai and Dmitry Anosov. But in the Soviet environment, he could not have access to the position he deserved on the basis of his competence because he was a Jew. In 1979, he decided to ask for the permission to emigrate with his family, a dramatic decision. He could do it successfully, spending some time at IHS, the institute I was director, not at that time, on his way to the US, instead of going to Israel, where he finally settled. Misha Brin was working on questions not too far from my own subject, and we sympathized through common friends. The following years, he visited IHS several times. In the early 1990s, his son, Sergei, born in 1973, started graduate school in Stanford under the guidance of Hector Garcia Molina, a Mexican computer scientist. Shortly before 1976, Sergei started to work with his friend Larry Page to develop a piece of software called PageRank, which, as its name suggests, orders websites using a process which attributes values to links. This was done with the help of a few mathematically oriented friends. The attempt was done taking a route using random programming rather different from the most popular programs available at this time. PageRank was finally successfully patented by Stanford University in 2001 with privileged access to the company Brin and Page had created in 1998, Google, not 30 years ago. The rest, of course, is history, as PageRank proved to be a breakthrough tool giving a competitive edge to Google. I still remember Misha, Sergey's father, complaining that the computer science PhD of his son was not moving quickly enough to his taste because of other occupations. He later changed his mind about that. Actually, when looks back, one can trace as an ancestor to PageRank as far as the late 19th century. It was used to rank competitors in a chess tournament. More closely to our time, in the late 1970s, programs used in scientometrics had similar objectives. Of course, the proliferation of websites, which has accompanied the development of internet, provided a new basic world to explore and to develop business with and about. Note, though, that what lies at the heart of the success of PageRank is just a piece of clever mathematics. It is now time for me to bring into the discussion my third lens, namely to take advantage of new technological developments. The extraordinary developments that we have been witnessing since the beginning of the 21st century are also directly linked to other parts of science and engineering, in particular to physics, with a revolution brought by the miniaturization of silicon chips. This led to an incredible increase in the computing capacity and speed, as well as a radical decrease in the cost of machines performing these calculations. This change of scale is, of course, what made the difference and gave the possibility to attract massive amounts of capital because of the expectations of very profitable business. This could only be done because the markets which would be developed around these new possibilities were of an unprecedented size. To take advantage of this new economy completely, new economic models needed to be built, and they were. And this continues. With the perspective of taking advantage of the second quantum revolution, which has to do with information, to develop a totally new type of computers. This is not yet done, but very significant progress is already at hand, not only on the physical side, but also on the concepts needed to manipulate qubits, the elementary pieces of information in this highly sophisticated scientific environment, mixing intimately very theoretical and very practical parts. Clearly, in this context, taking only a short-term view is almost certainly a losing strategy, as keeping an ambitious and open view is likely to provide a good surprise. How can one hope to be successful? For that, one needs to cultivate an ecosystem spanning from very fundamental science to the most concrete approach. At the European level, the establishment by Carlos Moedas of the European Commission Innovation Council, EIC, when he was the European Commissioner in charge of research and innovation, based on the success of the European Research Council, ERC, was governed by these principles. This was reinforced by the fact that from day one, the ERC Scientific Council, which has the responsibility of defining its strategy, worked hand in hand with the EIC board. This resulted, for example, in the decision by the EIC board to create a so-called transition program focused on helping projects from research teams to develop at their initiative innovations stemming from their discoveries. The majority of projects supported by it have been coming from ERC teams. My strong belief is that fundamentally it is always people who really make the difference, hence the need in any program to always keep a bottom-up part left at the initiative of actors. In this context, it is absolutely key to motivate people from the next generation. And for that, To present them with credible perspectives for a career, they must be able to shape their dreams in a supportive environment. This hope component must not be neglected. Are we doing that at the moment in Europe? I have my doubts, as is shown, for example, by the great difficulty to transform quickly enough into reality the pressing and well-documented demands made by the Letta and Draghi reports. It is time for me to come to my conclusion. In the introduction of his book, Mathematics as Metaphor, the late mathematician Yuri Manin writes, I'm quoting, "My whole intellectual life was informed by what I have gradually learned to identify as the Great Enlightenment Project. Crudely put, it is based upon the belief that human reason has the highest value, and that the expansion of knowledge and education will automatically produce better human beings living a better life." And here is the way it continues. The last century, the 20th, was a time where reason and unreason, equally strong, were developing and coexisting in a monstrously disharmonic symphony. Along with their more beneficial effects, science, politics, and art provided humanity with weapons of mass destruction, highly efficient totalitarian forms of self-organization, and the malicious glorification of all of this. Still, I trust in the Enlightenment project. End of quote. It looks like the present century is on its way to surpass in horror what the previous century has produced. The unprecedented power reached by technology moguls, conjugated with the too widespread lack of respect for facts and free thinking, makes the threat of a new dimension. We must realize this and organize ourselves to overcome this major challenge. I too trust the Enlightenment project, and I'm determined to fight for it against obscurantism and the domination of anti-scientific, nationalist, and authoritarian views. In the late 18th century, Denis Diderot was a great actor of the Enlightenment. He conducted the formidable project of l'Encyclopédie with Jean-Laurent d'Alembert, dedicated to making all forms of knowledge broadly available. It mobilized many people, including artists, to design the marvelous plates which illustrate it. We should not forget that this led Diderot to be jailed, because his brilliant writings were considered offensive by the church. In 2026, one celebrates, by the way, 250 years of the Entretien d'un philosophe avec la Maréchale d'Eu, his remarkable apology of atheism. Freedom of opinion has always been a fight, and it remains so. It is only by giving value to all forms of knowledge that one has a chance to tackle these big challenges we face presently and to get the next generation on board for that. Mathematics has its place in this mountain of knowledge, but without hope, it will not be possible to put it to use for the overall benefit of mankind. I thank you for your attention.
Thank you, Professor Bouillon, for that very important words. So we'll now have the intervention of Professor Nguyen Tien Dung, to whom I apologize for my pronunciation of his name. An international recognized mathematician for his contributions to symplectic topology, integrable Hamilton systems, and Poisson geometry. After a successful academic career, including positions in France and various places in Asia, he found Torus AI in 2019, where he serves as CEO and Chief Scientific Officer. Through Torus AI, he applies mathematical thinking to artificial intelligence, signal processing, and generative models, actively promoting an ethical and impact-oriented vision of technology. His trajectory exemplifies how a deep mathematical understanding can drive innovation through academia. Professor Nguyen, the stage is yours.
Thank you very much for the invitation, and And so it is my great honor to be here, and so thank you all. Do you hear me? Yeah? Okay, so yes, so I'm supposed to talk a bit about the mathematics in the age of AI, okay? So why should we still learn mathematics, and why should we still do mathematics in the age of AI, yeah? Because I heard many people saying that, well, AI already knows everything. We do not need to learn mathematics anymore. And they say actually the same thing about language, about whatever, right? So basically, we do not need to learn anything at all. And if we follow that reasoning, we will become very dumb, while the AI will become very smart. So it is not a very good, let's say, future for us, right? So in order not to become dumber and dumber, maybe we just need to learn something, right? Including mathematics, okay? So before talking about the AI, I would like to talk about just mathematics, okay? So why do people learn mathematics? So basically, I think that there are two main reasons. So one of the reasons, actually, my colleagues here already said many times about, is that the mathematics is a key to understand the world, right? It is the language of the universe. So in particular, the number pi, you go to Mars, the number pi will remain the same. To another galaxy, it will remain exactly the same. So those are universal things. And in order to understand physics and chemistry, I don't know, whatever, even social science, we need mathematical concepts, right? For example, understand, I don't know, whatever, in physics, you need some group theory in order to understand some real physics. Yeah. So, as Jean-Pierre said, maybe the ultimate goal is to become enlightened, right? And so I mean, you cannot become really enlightened without any mathematics. And so that's the first goal, is to understand the world. And the second goal, I think it might be a bit more basic, is to develop our own brain. And I think it is very important. So in school, I mean, if people ask school teachers why children should learn mathematics, and maybe it is not to do mathematics, it is to develop the brain, which is the most important thing here. And actually, the neuroscientists, they did a lot of experiments, right? And studies about what do people who learn mathematics gain, right, in learning mathematics. So they compared a group of people who learn math, is noted as M here, group of people who know mathematics, and a control group of also very good people, but who didn't have, like, say, very big math learning. And then they ask all kinds of questions to see how their brain works, right? Is there any difference in their brain, right, between these two groups? And what they found out is that for the group of people who did learn good mathematics, I mean, like a lot of mathematics, there are specific regions of the brain that are really developed. Okay, and so you can call these, let's say, blue regions as the mathematical brain, and the green regions here are like the semantic brain. Okay, so people who are very good at, I don't know, history, politics, whatever. So when they ask it all kind of questions, they always think with their semantic brain. But when people with a mathematical background, when they ask questions about, I don't know, the normal questions, they also use the semantic brain. But when they ask questions about the logical question or the strategy thinking, they will use another brain, which is the mathematical brain. And this gives them a kind of advantage because they have a kind of, I don't know, a GPU, CPU, or whatever processing units. And so mathematical learning gives you an additional processing unit in your brain. And it is a very good advantage that the mathematician, I mean, not the mathematicians, but the people who have good mathematical learning may have as an advantage when it comes to logical thinking in general, not just mathematical question, logical thinking, strategical thinking. So it is a very important point why we want to learn mathematics, okay? And okay, so these are the two main reasons. I think that this may keep people, I mean, children interested in learning mathematics, okay? And now why we do mathematics as professional mathematicians, right? So I just talked with Jean-Pierre during the lunch about a famous French minister who had a very kind of bad view about mathematicians, right? And he thought that mathematicians were useless. Right? And I think that in the world there are many ministers who act this way. They think that we should not hire mathematicians because they are basically useless. They waste money of the state, etc. Okay, but we try to refute that kind of opinion. And yeah, so okay, so actually, mathematics matter a lot. Okay, in engineering, all kind of science, etc., and also in AI, of course. Okay, so I came from. Actually, I'm still professor of mathematics, and I will still teach next year. But in my little company, half of the people have a PhD in mathematics, and we like that way because they really are good at building algorithms. So basically, AI means algorithm, okay, built in a certain way, and it becomes AI. But without understanding of I don't know, of fundamental thing, you cannot be good algorithm. You can copy from someone, but if it doesn't work, you do not know how to change this, how to make it work better. In order to understand really how the algorithm works, you would need some mathematical thinking anyway. Okay, so it gives you an edge when doing AI also. But of course, mathematics is also a kind of sport for us because as a professional mathematician, I know that when I prove a chance, oh, this wonderful thing, and I don't think many people can have this kind of sensation of happiness when you discover something in mathematics. It is really a kind of sport, and so a kind of art because when we discover something beautiful, we feel it, we feel the beauty. And as I don't know, Hardy said, or somebody said that beauty is the first test. So when you have something beautiful, it will be useful. So yeah, and yeah. So first, yes. So let's say theoretical mathematicians will do things that they think are beautiful. Okay, and then it will become useful, as George said about the theorem of Kolmogorov-Agnon. Right? At that time, they never knew that it would be used as the basis of neural networks. Right? Yeah, and yeah. So this is why we learn and do mathematics and. Yes, and eventually mathematics will be useful. Before the age of AI, I will talk about after the age of AI, it will remain useful, okay? And yeah, so now there is this scary new circulating around now is that the moment of AI singularity is arriving. And it is arriving faster than anybody could think, okay? Do you know this singularity, what does it mean? No, okay, so it means the following thing. It means that the AI becomes better than humans in almost everything, first thing. And the second thing is that the AI improves itself, okay, faster than humans can do. Actually, it is already happening. You know, this thing from Anthropic called the Cloud, Opus Cloud. So actually, Cloud rewrite itself, it is code. So the code of Cloud is written by Cloud. And every iteration, it becomes better and better, okay? And Cloud is now so powerful, and Cloud is used in the war in Iran, you know, right now, and there is a big scandal about it, etc. Okay. So now this is very scary because AI is really becoming, and it's already almost right now. They say that this singularity moment is arriving this year. Right? This is not some science fiction. It is that it is better than humans in almost every field. Okay, so we did a bit. Let's say we did a bit of medical stuff, and we know that our AI is much better than the doctors that we could measure. Okay, for example, and the reason is very simple. AI could learn from thousands of doctors. One doctor, maybe he could have, let's say, several thousand patients during all his professional life. Okay, one AI could learn from millions of cases, and of course it is better. Okay, I mean, it could be surprising, it would not be better, okay? It is natural for the AI to be better than people because it could learn from so many people, etc., from so many cases. Of course, it also needs good data, but another thing, okay? But theoretically, it is very easy to explain why AI can become better than human in almost everything, including fundamental research, including mathematics. So already right now, you know, Terence Tao, right? He says that AI is his junior assistant or whatever, right? I also have a very close personal friend, mathematician. She just wrote a paper, published it, on arXiv this month, okay? And in the paper, she gave thanks to Gemini, Grok, ChatGPT, like she co-author, right? That gave her ideas and then some parts of the proof of thing, right? So AI right now already could do cohomology, things like that, non-trivial cohomology, okay? It is not just Olympiad problem, but real mathematical research, okay? And of course, the consequence could be, might be, I don't know, they're not that, but might be scary. I mean, AI will replace most of the jobs. I mean, who need lawyers? If you have an AI assistant who is better than your lawyer, who need lawyer, okay? Who need accounting people because AI can do all the accounting for you, right? Who need mathematicians? So it is this scary picture that the AI going to replace most people, most jobs, and so we become slaves of AI, okay? But I would rather think about another scenario, which is much more optimistic, okay? It's that the AI is still controlled by us, and it is a tool that helps us become much more prosperous and much more enlightened. And this is the second scenario that I would like to mention about. So already some centuries ago, people they broke the machine. I mean, they just because they didn't like the fact that the machine could replace people, right, during the Industrial Revolution. Okay, but of course nobody would want to work the field without a machine now. Okay, because people can only do this much plus the machine we can do like that much more. Okay, let's say one part of the job is done by the people and 9 parts of the job done by the machine right now. So it is 10. So we have like 10 units of WANs, right? So it is now. But with the AI, it is 1 plus 999. Okay, so we do one part and the AI will do 999. Okay, so it means that our WANs will increase, let's say, 100-fold thanks to the AI. Not in a very long time. I mean, like during the next 1 or 2 decades, it's already like that. So it means that the WANs produced by the people will not decrease. I mean, by the people, by ourselves, but the part produced by the AI will becomes much bigger than before, so that the whole WANs will become much bigger, and this prosperity gives us time to take care of ourselves, to learn more, to become more intelligent, etc. So the whole world will become prosperous if we can control the AI. Of course, okay, it must be an ethical AI. Everything will be fine. And then there is this another problem about if the AI is become so intelligent, superhuman intelligent, should we be afraid of the AI? Okay, so we look so stupid compared to the AI, right? So you have all these kind of droids that are much more intelligent than us. Okay, so what should we do about the fact that you have some robots that are much more intelligent than we are? I mean, it is a reality. Okay, you cannot be compared to all these kind of droids. Now, okay, to think about it, but to think about the fact that the AI will become much more intelligent than us, we have to know one thing already, that our intelligence is tiny in the world. In any way, okay? What we know is really tiny. AI or not AI, the intelligence of the universe is huge compared to what we can know, what we can learn, okay? So, I mean, it is very probable that there are some other civilizations in some other galaxy who are 1,000 times more intelligent than we humans. It is, I mean, it is very probable, right? There may be thousands and thousands of planets with other civilizations somewhere in the universe, and they are most probably, some of them are much more intelligent than we. Okay, so it is not, I'd say, not a disaster at all, okay? So if we believe in some kind of God, the universe knows all, and so in any way, our intelligence is tiny, and even the superhuman intelligence is also tiny, okay? So we should not worry about the fact that there is some intelligence which is more intelligent than us, right? We should really worry only about ourselves, okay? And this universal intelligence is friendly. We still need because the world is friendly, right? Otherwise we would not exist, okay? So there is no reason to think that AI will not be friendly to us, right? So if it can be controlled by us, and everything will be fine. It will be a friendly intelligence, and we can use this intelligence. But so, okay, let's go back to mathematics now, okay? So mathematics is the age of AI. I think that the 2 reasons why we should, or children should learn AI, remain exactly the same in the age of AI, okay? So we have to learn mathematics to develop our brain. Not only mathematics, but other subjects too, language, other things. But mathematics is it's an integral part of it, okay? We should learn mathematics just to develop ourselves. and to understand the world. So these two reasons remain exactly the same, right? AI or no AI. Okay? And then why should we do mathematics? I mean, why there should still be mathematicians, right? But actually, if you look at the whole world, so there are only two scenarios. Either there will be almost no job, right? People will become obsolete. Or most of the jobs will stay, right? People still have activity, but aided by AI, right? So in the new world, post-AI age, actually all the activity will be there, but only people will work differently. People will be, the activity will be conducted different with the aid of AI. So everybody will use AI. So in particular, the mathematician will also use AI, okay, to do mathematics. Okay. Now, of course, you can leave it to AI to do the mathematics by itself, but most of that mathematics will be not relevant to the humans. Is that clear? Okay. The AI can invent all kinds of mathematics, but it will not be relevant. Now, if you know about the software world, most of the software solutions they fail not because they are not good. It is because they are irrelevant to the people. The people do not know how to use the software. That's why the software fails. Okay, here's the same. The AI can create anything the AI wants, but if it's not relevant to us, then it doesn't matter. So actually, we will need mathematicians to guide the AI to create mathematics together with the AI, so that mathematics will be relevant to the humanity. And that's the reason why we still need mathematicians. Okay, we still develop theory, theorem, whatever, with the help of the AI, okay? But those concept, theory, theorem, things will be relevant to us, right? That's the important thing. So, thank you.
Thank you, Professor Nguyen. So we go to our next speaker, Professor Eugênio Rocha. He's Associate Professor of Mathematics at the University of Aveiro and is the current president of the Portuguese Mathematical Society. With academic training in artificial intelligence, mathematics, and nonlinear control theory, his work encompasses both theoretical and applied mathematics. He has numerous publications in areas such as differential equations, optimization, control theory, and mathematical modeling, with applications ranging from biology and epidemiology to engineering, economics, and education. Alongside his academic work, he has played a central role in coordinating multidisciplinary teams in large-scale projects in areas of manufacturing, logistics, data science, and machine learning, illustrating how mathematics serves as a bridge between theory, computation, and innovation. Eugênio?
Thank you so much for this nice presentation. So it's a privilege and an honor to be here. Thank you for the invitation. So good afternoon, everyone. In my presentation, I'm going to focus on real examples that are just limited to my team. And my purpose will be twofold. One is to destroy somehow or convince you that the myth that new mathematics take too long to go to products is false. So we can, in fact, create new mathematics and put it in production very fast. This is the first one. The second one is to try in a high level to share my very particular opinion about the ingredients that are key for innovation in my particular point of view. And these key ingredients are three. One is deep knowledge, the other one is cross-disciplinarity, and the other one is what I call the role of a science integrator, okay? That I will explain a little bit. So let me start with the definition. I'm a mathematician, so I like definitions. So there are several definitions for these. Let me fix for these two. So invention is the creation of new knowledge, process, or products. Innovation is the practical application of ideas that result in delivery of new value. Okay? This is important for mathematicians to take care. Now let us look. I will go through the innovation equation, but let me go to the last pillar. The last pillar is viability. And viability, one of the pillars of innovation, tell you that is there a sustainable model for keep going, so generating value. Now you can ask, does fundamental science as mathematics play any role in innovation? If we look for the definition, okay? So let me be a little bit provocative because we have here the minister, okay? And the minister will, for sure, detect some mistakes here. For example, that agendas PRR, they are under ANI, but in fact, they are coordinated by IAPMEI, but there is some kind of administration conjunction. But so we had these three institutions. So let me say, the first one was focused on deep knowledge and research. And one key point was without immediate commercial pressure. The second one was more knowledge transfer and innovation. And the last one is more business competitiveness and market scaling. So more or less, let us simplify like foundation, bridge, and market. And now you put mathematics. And mathematics, if you think a little bit, it's just on the first side. So how mathematics can go to innovation, okay? Now, when we mix this, so if we mix, oh, sorry.
Just to send to the Secretary of State.
Oh, sorry. Can I go back? Oh, Can you go back, please? More? Yes, thank you. Thank you. So, let me continue. So, mathematics is quite related with deep knowledge, okay? And you have innovation that is deliver of new value, okay? And that's the reason why in the last months, mathematicians will have a natural concern, okay? That is, maybe we will have mainly support for useful mathematics. So what I want to point out is not this. What I want to point out is that we need to look things in a little different point of view. What is the point of view? I'm going to share only my experience with my team, okay? So as good as bad as it is. So I have some experience in coordinating agendas and also other types of projects, okay? So in particular, let us focus on agendas. I coordinate these agendas. So Nexus is a logistic agenda. So it's all the supply chain from Port of Sines to your house, last mile, okay? So with 35 partners. And then we have this agenda that is Alliance, that is more related with gadgets in houses, like Bosch thermotechnology, like heat pumps and so on. So let me share my very particular ideas. First thing, work packages. Structure promotes multidisciplinarity and not cross-disciplinarity. And this is a key structure for the projects, okay? First one. Second one, deep knowledge groups still do not participate as they should, okay? The other one is deep knowledge groups need to go deeper instead of trying to be applied. It's very good and we like very much to be applied, but my opinion is we need to go deeper, more theoretical. Let me explain why. And then, this is a very little one, regular deliverables and milestones do not ensure project excellence for sure. And we have a lot of work with that. And so, what is the difference for me between multidisciplinarity and cross-disciplinarity? So, multiple disciplines working on the same problem independently within their own silos. So, experts collaborate side by side, but stay within their boundaries. So, an analogy is like a fruit salad. In a fruit salad, you have a lot of fruits. They are together, but every fruit, it's its own fruit. Okay? What I believe, we should not go for fruit salads. What is the idea? The idea is to use cross-disciplinary. So what is? Viewing one discipline through the length and tools of another. Means that boundaries should be blurred and methods from field A should be used to solve field B. Okay? And I'm going to share with you I will try to convince you, not by zero knowledge because I need to share information, also not by a traditional proof, okay, but by examples, only my examples here. Let me show you my team. In fact, it's bigger, but these are some elements. So one key point is that I supervise master theses, PhDs, and postdocs from all these fields, okay? So mathematics, mechanical engineer, data science, industrial management, physical and computational engineer, and informatics. And in the team, we have several ways to look to things. One is that, as we like for these guys, they should be very good, so good deep knowledge. They should be good at the field. That is natural. The other thing is that the team follows cross-disciplinarity. What it means? It means that a mathematician looks to the problem of the guy of industrial engineer, and the industrial engineer looks to the mathematics, always. We are always thinking like that, okay? The other thing is we have a science integrator. What it means in a very simple way. In this case is this guy, but this guy has the fortune to know a little bit about mathematics, data science, and informatics. So can go through the several topics, okay? So let us go to examples so I convince you that this approach more or less is effective. The first one example is 2022. And this is a work that we did for manufacturing. So it was done in OLI. So it's me, a guy from OLI, and a PhD students from engineer mechanicals, or mechanical engineer. So what we did with mathematics, for sure, new algorithm mixing statistics, logics, function analysis, and plus anomaly detection. And the big setting was we pick these fault trees that in fact are trees where the nodes, middle nodes are operators, logical operators. In the basis you have distributions, and then we consider these operators like operators in a Banach space and play a little bit with function analysis. What is the result? The result is in OLI, in real data. In fact, this was injection machines that we received 400 values 20 times per second. So it's big data, okay, for sure. And we were able to reduce 27% for preventive maintenance and 63% for corrective maintenance. The result, we won a prize, okay, I can tell you. We won a prize in a conference in Austria with 150 papers, and that was the best paper, okay? With more than 100 institutions competing. So, another example. This is a different one, logistics, okay? 2023, so 2023. So, Synchromodal transport system. So here, what is the idea? The idea of just doing mathematics, doing the informatics, and putting everything in an edge device. So we had a new algorithm for data-driven algorithm. So detects when data just drifts. What it means, we can have sensors, and then we have an algorithm that detects when we need to send information to the central. So it's not beeping every time. It just detects in real time when it's important or not. Okay? These sensors were put in containers and trucks. So that's the first thing. This has 3 modules. The second module is a novel benchmarking approach to measure multi-objective efficiency. So how to measure efficiency in the correct way. And then the final, it's a novel real-time scheduling and assignment model for using CP-SAT solvers for the people that like about this. So what is the result? High improvements in transportation planning and detail-efficient analysis. Here the issue is we consider several freights, so several enterprises that have their tracks and they don't need to share data. One of the issues in logistics is you need to develop results algorithms for which you do not share data, at least not raw data. Otherwise, no one is going to play with you because that is the value of logistics, in fact, okay? So we, in 23, we received the best work of the International Federation of Logistics and Supply Chain in South Korea. Okay? Now to 2024. So now health. Progression and age-related macular degeneration disease. So this is done with EBLE in Coimbra, so with ophthalmologists, doctors, okay? And we develop a new algorithm to determine root cause and prediction of the disease and how they progress somehow, okay? And this is a mix of probability, belief propagation, and again, function analysis. Why function analysis? Because I like very much PDEs, I work in PDEs, so function analysis somehow appears everywhere because I push, it should be there, okay? But in fact, it's very useful. So in this case, we won in this year the prize of Nascimento Leitão and Bayer prize. So that was the prize of that year. So next year, we are almost into 26. So 25. PhD thesis is about continuous improvement on companies. Now is management, okay? So completely different areas. We are just talking about big data, how big data can be used in an effective way in the context of enterprises, okay? And here we have, in fact, a very long platform, very descriptive of how big data should be used and how should be implemented, and also has several real applications. The applications were done in Bosch, were done in Vista Alegre, were done in Port of Sines, and so on. So every time is tested with real data, okay? So here, for example, one novel algorithm for bottleneck identification. And the key point is use minimal information. Why minimal information? Means that if you are not advanced, you want to implement some IoT and put sensors, that is the minimal quantity of sensors that you need to put to ensure that you have a bottleneck algorithm to work, okay? So that's, it's a thesis that in fact receives 2 prizes. One prize is supported by Airbus and was given by Industrial Engineering Operations Management Society in Paris, in France. The other one, this was more related with the part of industrial parts, the applications to the industry, and then receives the Portuguese Association for Quality in Madeira, more related with the management and the application of big data. Now, this year. So this year, we believe we have something interesting, and this is a novel data streaming machine learning model, let us say. So this is data science, using mathematics to change algorithms to have new models for data science. And the key point is there is the notion of entropy and several generalizations, in fact, and we did an ultra generalization of all these models of entropies. So in fact, our entropy has 5 parameters. So it's not nice, and uses quantum calculus. So it's not beautiful. But the issue is when we try to apply to very difficult problems in machine learning, like benchmarking real data, it overpasses all the algorithms that we know. So it should be relevant somehow. We are just trying to improve industrial products in this sense because it should be useful for the difficult real problems. So again, I try to show you by example that somehow what I believe is every mathematician should be as good as possible in their field. Then to be applied, what happens is we need this role that sometimes I don't think is quite common, that is a science integrated, that has this view, that has a big, broad view and knowledge to just see things from the lens of the others and then play together, and not the fruit salad that usually we have in several of these projects, okay? As you understand, you give me 50 minutes, so I talked about good things in my team. If you give me 1 hour, I can talk about everything that does not work, okay? So I have a lot that did not work and does not work, okay? So, to finish, we will have in June from 3 to 7 some events. a summit of manufacturing and logistics for companies, industry, to come and discuss. We have 2 conferences to meet together, people from theoretics and practical and so on. And also we will have the demonstrator where you can see all of these products working. In particular, this is a control tower for the first part of the Port of Sines. So, thank you.
Thank you, Eugene, for the nice presentation. So to conclude this segment of interventions from our guests, we have with us Professor Pedro Camanho. He's Professor of Mechanical Engineering at the University of Porto, and is another doctorate from Imperial College today. I think it's the second one we have here. And an internationally recognized expert in advanced composite material mechanics. His work is strongly based on mathematical modeling and computational mechanics, and has been successfully transposed to industry with methods implemented by widely used engineering software. A former leader of important research institutions and programs, he has received numerous international distinctions, including a recent European Research Council Advanced Grant at the forefront of its technological innovation. Professor Pedro Camanho, the stage is yours. We are only about 10-15 minutes late, which is very impressive, and that's because we are mathematicians, okay? Not perfect, but getting there.
Okay, good afternoon, and thank you very much for the invitation. I'd like to thank the Professor Jorge Milhazes, Lisbon Academy of Sciences and the International Center of Mathematics for the invitation and for being bold enough to invite an engineer to talk during the International Day of Mathematics. So I like very much the topic of this day, mathematics and hope. And we as humans, when we think about hope, we think about a better future, or at least a more sustainable future. And that means that we need to answer a fundamental question, that is how to ensure that the human developed system during the last 10,000 years, developed since we invented agriculture, can coexist with the natural and biological world that developed during thousands of millions of years. And just to give you a perspective of this, of the relevance of this question, let's consider that we as human beings, we need 2,000 calories per day to survive. That means that our metabolic rate is about 90 watts. But of course, we don't just use energy to survive. We have what we call the social rate as well. And the social metabolic rate of an average American, it's 11,000 watts. That corresponds to the biological rate of 12 adult elephants. So if we consider that there are 350 million Americans and only 500,000 elephants, we can see the pressure that we're putting in terms of energy supply and the pollution that comes with that. And I'll try to explain how mathematics can be used to tackle and to mitigate this problem. But let me start with the 2 assumptions that it's really from my perception as an engineer of the role of mathematics. And the first one is that I believe that all the scientific fields from social sciences to physics to biology are connected. So the Harvard zoologist Edward Wilson, he took this idea to a limit. He proposed a theory that unifies all the scientific fields. But in any case, my view is that the great unifier of all the scientific fields is mathematics. So the second assumption is related with the fact that, notwithstanding the fact that we have unprecedented levels of publications and patents, scientific progress is slowing down. So, and I believe that the great enabler of disruptive science is mathematics. And I'll try to elaborate a little bit on these 2 topics during my presentation. So as it was said in the kind introduction that was made, I work in the aerospace field, and of course, we all benefit from aerospace, but we need to understand that also the aerospace field is putting some pressure in the environment. And you can see here the predicted emissions of CO2 throughout the years. Of course, there was a decrease there due to COVID, but if we don't do anything, we'll reach and acceptable levels of pollution by 2050, about 2,000 millions of tons of CO2 emissions from commercial aviation alone. So, and you can see that the European Union set this goal of having net zero emissions from commercial aviation by 2050. And the way to reach this goal, it's very much supported on development of sustainable aviation fuels that will put the burden elsewhere, but I will not discuss that here. But you can see that about 22% relies on technology. And technology, we are basically talking about three things. The first one is more efficient engines. The second one is better aerodynamics, and the third one is new lightweight materials. But we need to understand that the two first topics rely on the third. So we cannot have better aerodynamics and we cannot have better and more efficient engines without the use of new lightweight materials. And these materials are mainly fiber reinforced polymers. And we need to develop a new generation of not only fiber reinforced polymers, but also of methods to design with these new materials. And the main question that we have to tackle is really how the modifications and the manipulations that we can do at the molecular level or at the micromechanical level will affect the structural performance of a composite wing or a fuselage. So we need to establish these relations to be able to develop new materials. And this is really the main topic of my ERC Advanced grant. And once we establish this understanding, then we can concurrently optimize at the molecular level, the microstructure and the topology of an aircraft with respect to the main design drivers. Now, as I've mentioned, this goal relies on the use of polymer composite materials. And they have a problem because they are brittle. Of course, we don't like to have catastrophic structural failures in aircraft. And if you look at the stress-strain relation when we test these materials, you can see in blue that the relation is linear, which we don't like because we'd like to have some ductility so that we can have some possibilities to design for damage tolerance. The question is how to make something that is very brittle into a ductile material, okay? We use a combination of experimental observations and mathematics because if we test a single carbon fiber, you can see there, or maybe you can't because the diameter is just 5 microns, but we tested different families of carbon fibers that were produced in different ways. And we have the available plots for the distribution of the strengths of fibers that were processed in different ways. And our hypothesis is that if we introduce or if we commingle these different type of fibers, we can get ductility. And indeed, from some previous simulations that we did with a perfect microstructure, you can see that we can predict something that is more ductile. So you can see that we are bringing ductility into a material that is very, very brittle, which means that we use mathematics as a trigger to imagine new materials with counterintuitive properties. So without mathematics, we would not be able to imagine the possibility to develop these new materials. Now, of course, this microstructure that you see there, it's very perfect, but perfection only exists in mathematics, not in real life. So when we are then going to the lab and we try to manufacture these materials, you can see that we don't get this nice distribution. And then we have another problem because I'm using two different types of carbon fibers. We use X-ray microscopy, so we have basically the same X-ray absorption from the different fibers, and I cannot tell one from the other. So how can I, if I cannot visualize, I cannot simulate. So I cannot progress on the study. So again, I use mathematics to solve the problem. So we use a convolutional neural network to really segment, and you can see now in different colors that we can identify now the different type of fibers, which means that I also use mathematics to observe what is impossible to distinguish using the human eye, okay? So, and now we can move to the next level, now that I can separate the different constituents, and I can start and simulate the way that this material deforms and fails. So what you see here is really the result of an experiment that we conducted inside a scanning electronic microscope, but basically I'm plotting the way that the material stretches along that line segment over there. And here, this is the results, and you can see in red the experimental result of the strain that the materials experience. And in black, you can see the prediction from classical solid-state physics. And you can see that there's a huge error, which led us to the hypothesis that classical physics or classical solid-state physics do not apply at very small scale. So we are challenging what is called the principle of local effect, which means that typically it is assumed that the deformation state at a given point depends on the history of deformation at that given material point, but we are arguing that it also depends on the vicinity, so the neighbors will play a role. And to represent that, we use an Helmholtz equation. So there's a length scale that we introduced in our constitutive formulation, and we have this Helmholtz equation, and you can see that if we now assume that there's this no locality in the material behavior, we can capture perfectly the experimental observations, which means, again, that we use also mathematics to describe in a rigorous way new laws of physics. Right, now that we have the proper models at this scale, we can go ahead and try to upscale our simulations, because of course we need to design wings and fuselage and different structural components. And one technology that is really has the potential to be disruptive, but it has been lingering for over 20 years, is multiscale analysis. So the mathematical formalism to link the scale, for example, if we have a stringer and we go down to the microstructure and we pass the information back and forth, that has been established a long time ago. But this, so far, has been just a toy problem or a very academic problem due to the cost of computations at the micro scale. So I did an exercise with Airbus to size a stringer using multi-scale analysis and using the high-performance computers that they have available at Airbus, accounting for uncertainties, which means that we need to use Monte Carlo methods as well. It would take 50 years. That means that I would launch the simulation today, and then my son will post-process the results, right? So it's like a toy problem, but this is critical for the future of aircraft design. So the initial idea that we had was to replace the computational model of the microstructure with a neural network. But quickly we realized that we're just putting the burden elsewhere. So instead of solving directly the problem using a multi-scale analysis, we were putting the burden in training a neural network with a path-dependent material response. So this will not solve the problem. But what does solve the problem, and this is a recent result, and this also highlights the importance of thinking mathematics and physics, is really to think of the neural network as something that not only has intelligence, but it has knowledge and memory. So we propose what we call a physically recurrent neural network, but basically what we do, instead of using a general transfer function, we actually put the physical models inside the neural network. So we have the constitutive models for the fiber, for the resin, everything. So we have knowledge inside it, and we have memory inside the neural network, and you can see that we can predict this complex path-dependent response very well. Which means, and that comes back to what I said at the beginning, that I see mathematics as the enabler of disruptive technology. So the very same problem that would take 50 years to run, I was able to solve it in 2 hours, okay? So it means that now we can use multi-scale analysis, which for the last 15 years at least, was, like I said, just an academic problem. Right, now we also need to understand that we have models, but we are applying these models in aircrafts that carry people and in other systems. And of course, there are uncertainties. So there are aleatory uncertainties because there are different conditions in the flight envelope. We have variability of the material, of the geometry, and we have also epistemic uncertainties because these are related with our models and with the fact that we don't know what we don't know. And the question is how to manage and quantify all these uncertainties. So we have been working with Airbus for many years on this question, and we came out with a workflow that is able to quantify and to manage uncertainties. So you can see that in this workflow, we need to quantify the uncertainties, we need to propagate the uncertainties, we need to use surrogate models. So all this framework heavily relies on mathematics. And one interesting result was the Vega C launcher, a launcher from the European Space Agency, that was the first system that was qualified by simulation. So our goal is to qualify and to certify by simulation supported by experiments rather than use experiments supported by simulation. Now you can see that this part that connects the 2 stages of the launcher was simulated, was certified. I asked Airbus because I knew that we would have some economists here listening to the presentation for some numbers related to the cost reductions, but they did not, they don't authorize me to share these numbers. But what is important is that there was a huge reduction in development cost, also a huge reduction in recurring costs of operation. And what they allowed me to share is the percentage of the reduction in terms of development time, which is very important, because if you lose time to market, you know, some competitors will come out with a better product sooner. So that means that we also use mathematics to instill confidence, to reduce recurring and development costs, and also time to market. Now, that brings me to the second part of my presentation, because I consider that these scientific developments and the associated technologies are necessary conditions for progress and to tackle this question about future sustainability, but they are not sufficient conditions. We cannot do anything without public engagement, right? And my hypothesis is that people and humans will try to protect what they like. So, and in that sense, recently I've published a book of underwater photography. It was published by Arte Ciência here at the University of Porto, and there's an exhibition of some of my photos in the Hall of Biodiversity. So if you have time, it's not far from here. Okay, let me go back here. And you may wonder what this has to do with mathematics. It has a lot to do with mathematics, because if we start with the Fibonacci sequence, that you know this better than me, right? So we start with 0 and 1, and we take the consecutive numbers of Fibonacci sequence as the sum of the two previous numbers, and that limit the ratio between the two Fibonacci numbers is called the golden ratio, so 1.618. So what we can do is to define this spiral where you have quarter of circles with the radius equal to the corresponding Fibonacci number. So we start with 1, 1, 2, 3, 5, 8, and 13, and we can use this to compose photography. Of course, this was not my idea. Leonardo da Vinci used this in this painting. The Greek architects used the concept of the golden ratio also in the Parthenon, and Debussy used also the golden ratio in his music. So you use it in space and in time, but I use it to compose photography, and this is one photo from my book where you can see that I have to take mathematics underwater, and I try to compose with this grid in my head, if the fish collaborate, which sometimes they don't, right? Now, what you can also do with Fibonacci sequence is to define this rectangle where the ratio between the two sides is, again, the golden ratio. And by these geometric constructions, you have two strong points that also you can use to compose. So, and this is the cover page of my book, and basically with what we do with mathematics, and also with light, and also with color, we're trying to guide the eyes of the readers to this particular point. So this also means that we can use mathematics to create beauty. Now, also we can see, observe animal behavior, and we can represent this behavior using mathematics. So, for example, some photos that I've made, you can see symmetry. You can see what I call emergent behavior. So this is for me, if you look at this school of fish, I also see a neural network, because they take decisions individually that are very simple, but collectively they can solve very complex problems. So the fish, the school of fish here, was getting into a shape that was meant to move me away, right? So, and this is emergent behavior in 2 dimensions, because even the stripes of the fish, they result from emergent behavior. There's a paper from Alan Turing that explains it, the chemical basis of morphogenesis, that explains that also the patterns result from emergent behavior. And also I can see fractals. When I photograph, for example, these coral reefs, you can see that we have a fractal structure. Now, what I'd like to say in terms of concluding my talk is that I don't see as an engineer mathematics as simply a tool for what I do, both in terms of my scientific activities and in terms of dissemination and photography. It's actually, I believe it's part of my nature. It's embedded in everything that I do. And again, I'd like to thank the invitation for giving this presentation.
Thank you. Very nice presentation. You just became my favorite engineer. That was an apology of mathematics. It was very nice. So now we have to make some change here on the stage. So let me first thank all the speakers for the generosity of sharing with us their ideas and pictures for inspiring presentations we just heard. So we're now going to enter the final part of this afternoon, which takes the form of a roundtable discussion that I will have the pleasure of moderating. I don't know if I'll have the pleasure, I'm a little bit afraid, but let's see how it goes. And which aims to encourage dialogue between different perspectives on how mathematics contributes to innovation, opportunity, and hope. And while the stage is mounted, I would like to thank the Minister of Education. We are honored to have you here today, to have spent the afternoon with us. So the Minister of Education, Science and Innovation, Professor Fernando Alexandre. He holds a PhD of Economics from Birkbeck College, University of London. So there's 3 people here from the University of London at least. And he's an Associate Professor of Rehabilitation at the University of Minho. He was Pro-Rector, Director of the School of Economics and Management, and Director of the Department of Economics. He was Secretary of State of the Portuguese government between 2013 and 2015. And he also served as Vice President of the Economic and Social Council. He's the author or co-author of several books, book chapters, and articles published in several prestigious journals in economy.